All right, now let's finally build this mux. One way that we could build this mux is by using if statements. So inside our comb block, we could write the following. This looks a lot like what we would write in an if statement in C. However, those curly brackets have been replaced by begin and end keywords. Begin and end are kind of just used to group blocks of code together in Verilog. And we have our Verilog literal for checking what select is equal to. So then we can go on to the next select value. Now this is quickly going to get messy, but you can see the idea. And you can see how we are describing this part of the circuit in a much more behavioral fashion than using those assign keywords. This looks more like code now, right? Now in these sorts of cases, it is far neater to use a case statement than lots of nested if statements. So let's do that instead. We can start by using the keyword case, open bracket, then the signal that we are considering in the case statement, in this case select, then close the bracket. Then we can finish the case statement with the keyword end case. Inside the case statement, we can put some logic for each of the possible values that select can have. Let's do this for the case when select is 0 to start with. So we write the value that the case statement can have, 3'D 0, colon, and then we can put our logic for what happens in that case. So we can put Q equals A here. Now let's do it for when select is 1. We write 3'D 1, colon, then Q equals B. If we wanted to do a more complicated bit of logic that required more than one line for each of the values of select, we could use those begin and end keywords to create a little block of Verilog code. However, in this case, we are just doing simple assignments, so we can omit them and keep our code neater. Let's complete the rest of the mux. Okay, great. Now let's make and compile. Oh no, it failed. And it says that case values are incompletely covered. What this means is that in our procedural block, we did not describe the logic for all possible input paths. So it's not defined very well. We've defined it a bit ambiguously. Now, this is a slightly tricky concept to get, but it's very important. When we are defining a circuit like this, we need to specify the behavior for all possible inputs. We can't have a case where we have an input value and the circuit doesn't know what to assign the output. If we look at this case statement, we have a problem. What happens when the select input is equal to 7? We don't give any outputs. One option might be to save the value of the previous time the circuit executed and return it. However, this requires special hardware known as a register. And it's kind of the only way that we can save state in our circuit. In order to use a register, we have to write code in a particular way, and we need extra things. We need something called a clock in our circuit. Now, registers are super important, and we will get onto them quite soon. However, for non-registered procedural blocks of code, we need to make sure that we explicitly state what the behavior is for every possible input. In this case, we need to say what the output will be when select equals 7. Looking back at our diagram, we can see that we forgot the case where we wanted the output to be a constant 42 when select was 7. So let's add that here. Okay, make and build again. Great, that fixed it. We fully and unambiguously describe the structure of our multiplexer. And looking at the waveform, we can indeed see that it is working correctly. Fantastic work reaching this milestone in your Verilog journey. This is a really important point. When we have a combinatorial procedural block of code, we need to make sure that we describe it fully and unambiguously. We need to make sure that the output is driven in every single possible combinations of the input. Okay, don't forget to give the exercise a try, and see you next time.